Well, hello, fifth grade math students, and welcome back to our study of Chapter 13, looking at triangles mostly so far. But in this lesson, we're going to move on to four-sided shapes, and we're going to start off by looking at parallelograms. Now, this is a longer part of our chapter that will take 3 days to get through. So that's going to be our entire week. And after that, we have been through all of the Chapter 13 material, and we'll be ready for a test next week. So start making sure that you're familiar with all the stuff that we did before spring break. Remember that the last day that we had class before break, I recorded a review of all the concepts we had done so far. So that is not a bad idea to go back and look at, especially as today your homework is quite light. But first, let's go through this lesson of looking at parallelograms. And ask yourself, if you're not on page 211 in your book already, you probably want to turn there. And as you're turning there, ask yourself, do you remember what makes a parallelogram unique? How do you know that it's a parallelogram or not? And the answer to that question is right in the word parallel. Remember, parallel lines are two lines that will never touch each other. So we have this shape here, A, B, C, D, that looks like it's probably a parallelogram. Here's how I'm going to test it using my ruler and my protractor. If I place both of these straight edges right on those sides, I can imagine that this line would go on forever. And I can see that this ruler, if it kept on going, and this straight edge of the protractor were extended, these lines are never going to meet. For me, using these two visually helps me to see what the direction that those lines or line segments are going. And I need to do the same thing on the other side, because both pairs need to be parallel in order to make it a parallelogram. And we can see here that yes, this one will also work. It will extend and never meet. I drew some examples for us here. Take a second and look at each of these three shapes and ask yourself which ones you think are a parallelogram and which one aren't. Or maybe they all are, or maybe they all aren't. Let's start with one that looks maybe like a little bit to be a shape that you know before, this square here. If I make these straight edges on both sides, that looks like they're not going to go on to meet. And same thing up there. So yes, not only is this a parallelogram or a square, but is also a parallelogram. Let's check this one up here. First, I'm going to check these sides. That seems to pass. Good. And then this one here. Ooh, actually, do you see how it's close? But there's a bigger gap up here than there is down here. So eventually, if I kept these lines going, these are going to meet further down. So no, this one is not a parallelogram. It only has one pair of parallel sides. This one down here looks good. And that one also looks good. So yes, this one is a parallelogram. And our check there is to make sure that the sides, both pairs, do not meet. For the next part, I've done this a few times before. We're actually going to look at some little cutouts of rhombuses that I've used. Ooh, the glare is pretty intense. Sorry about that. Here's what we're going to do. I'm actually going to cut these up. I'm going to cut them up in such a way that we can tell which sides were originally on the outside edge. So for example, this I'm going to cut all jagged like that. So it's pretty messy. So these sides I've really messed up and cut up. But go ahead and look at the side that I did not touch. Do you notice that they're the same length? What if I cut it the other way? So this is the same shape, but instead of cutting it through the middle this way, I'm going to cut it up and down. But same kind of jagged shape so I can remember which side is which. Oops. Now, any predictions? If I put these two sides next to each other, do you think they'll be the same? Let's go ahead and check. Yes, they are. So both shapes, they're originally the same. It didn't matter which middle I cut it through. The opposite sides of these rhombuses are the same length. And actually, if we go back to the problem that I started with today, If you count the squares for each of these, you'll see that the length of each of these are also equal. So there's a new rule for us about rhombuses. Opposite sides are going, not rhombus, parallelograms. Opposite sides of parallelograms are going to be equal to each other. Now there's also a unique thing going on with the angles. I want to give you a chance to try to figure that out first. Why don't you just look at those parallelograms and make any predictions that you think that I will show you about angles. You can pause if you want more time to think, but I'm going to go ahead and keep on going with the lesson and cut it up all jagged again so we can tell which side is which. Now your prediction may have had something to do with angles being equal to each other. How can I test without using a protractor if these are equal to each other? If I laid them on top of each other. So I'm going to take this one and lay it on top. And you see how that angle, they match up perfectly. They're the exact same size when I put them on top of each other. What about the longer pair of angles? Cut it up the other way and lay them on top of each other. Yes, again, not only are the sides the same length, you can see, but those angles fall exactly on top of each other. So this one I want to make sure we don't get too much glare. But you see how I've labeled each of these? Which angles would we assume are equal to each other in this parallelogram before I cut them all up? Now that I've got them labeled, I'm just going to cut it straight down the middle. If you're thinking the odd numbers were the same, let's test that. So here's my 1 angle and my 3 angle. Hold it up so you can see a little bit better. See how they perfectly land on top of each other. Same thing going on with these evens. Perfectly line up. Do you think there's any relationship between the odd and even numbers? Ooh, me holding it like this is kind of a hint. But look if you put them together. What does that look like? So there's a term that we've studied before. If you're thinking angles on a line, that is awesome. Those look like angles on a line to me. And actually, so do those. What if I put all those angles together? That looks like angles on a point. Again, I know the glare is a little bit hard to see, but the relationship we're starting to find is that the opposite angles, if I reassemble that original shape, don't know if I can. Well, if I did reassemble this shape, which I would do this one here. There we go. There's my original shape. The opposite angles we have found are equal to each other. And these opposite angles are equal to each other. And these two, if I add them together, are angles on a line. And these two are angles on a line. And because 2 and 4 are equal to each other, if I switch those, look at that. Those are also equal to each other. And 5th graders, this was all an exercise that was actually in your book on page 212 to 214. If you would like to do this on your own, you're absolutely welcome to. But let's just go back to that original shape that I was using. And things that we have learned from all of this is that this is equal to that opposite side. This side is equal to that side. These opposite angles are equal to each other. And so are those opposite angles. Those are some important relationships that are going to make it a lot easier to find out angles about parallelograms. And to prove it, let's do a few examples. These are also in your book. Looking at this parallelogram, if this is 80 degrees, what's the measure of that angle? If you're thinking 80 degrees, you would be correct, because that would be the opposite angle. Let's, for the sake of practice, let's see if we can say what these other two are. It's a little bit harder because it's not just equal to each other. What's the measure of this angle? Well, do you remember that angles on a line are equal to 180 degrees? So 180 minus that 80 would leave you with 100 degrees left. So this one would have to be 100 degrees as well. What about this? This is the guided practice number 3. This is 56 degrees. How large is this one? That's 180 minus 56, so that one has to be 124. So this one also has to be 124, which means that one has to be 56. And you notice how these are both acute angles and these are both obtuse? They're not drawn to scale, but it looks like it makes sense. Ooh, this one's getting a little bit harder. I have to find that one. They've told us this is 25 and that's 75. How can I do that? Well, if that's 75, what does this entire angle have to be? It must be 180 minus 75, or 105 degrees. That's this entire angle. But 25 of those degrees are right here. So this other part of the whole is 105 degrees minus 25 degrees, which is 80 degrees. So this question mark is equal to 80 degrees. And then finally, this is the other one that I want to look at together. This one is on page 216 of your book. Angle's 48 degrees. They want us to figure out what this one is. Now we actually know that this is 90 degrees because it's a right angle. So whatever this entire angle is, plus that angle equals 180. So 180 degrees minus 48 degrees leaves 132 degrees for this entire thing. But again, I got that right angle. So 132 degrees minus 90 degrees leaves 42 degrees for this angle there. Okay, so hopefully you're starting to get used to these opposite angles being equal to each other, and these angles, which we call adjacent angles, because they're next to each other. Adjacent angles are angles on a line. Your homework today is just the first couple pages of the workbook, pages 137 to 138. And we'll continue to work through this lesson for the rest of the week. And again, I also suggest that you go back and watch the review of all that we have been doing that I posted at the end of our last week before spring break. Let me know if you have any questions, and I look forward to our next Zoom session.